Today we'll discuss psychrometry, the wet air diagram. To discuss the humid air diagram, we must first talk about dry air. What is dry air? Dry air is a mixture of gases with varying weight percentages, including nitrogen, oxygen, carbon dioxide, hydrogen, and small amounts of rare gases. What properties do we want to know about dry air? Well, the specific volume, which is the volume per unit mass of a material, a strange concept linked to density, the mass per unit volume of a substance, and inversely related. Knowing specific volume, if we divide one by specific volume, we get density, and know if something or material is dense, if it weighs a lot, or if it's not very dense, if it weighs less, with same volume. Enthalpy, which is the amount of energy involved in processes, we will see later that with this, in the next video, we will see that with this we calculate the powers of cyclical processes, having air in certain conditions. If we take it to other conditions, that implies a power, either heat or cold, but it implies a power. Enthalpy determines the power or energy required to carry out a process and the input needed to initiate it. And the specific heat, which is a value that we could know. The psychrometric will not give it to us, but it is necessary, and at sea level it is 0.244 kilocalories per kilogram degree Celsius. This would be the table where we find these tabulated values. Depending on the dry temperature, we obtain a series of values, but in the end, this is very cumbersome, because we already have a table just for the dry air. If we take dry air and add water to it, the properties will change, and we will have a greater number of tables than before. Based on what? Based on the amount of water vapor that air contains, which is no longer dry, it is now humid air, but the amount of water vapor within the air is variable. As the properties are variable, they will change completely, which would give us a lot of tables, and it is cumbersome. That is why we collaborate with a diagram where we have many points and many tables that are contained within it. Table with saturated air, saturation temperature, air full of water vapor, cannot hold more water. Obtain another set of characteristics from the table for further analysis. In this diagram, the first table, which is the dry air table, would be just this line. With that, table says very little, but second table gives me saturated air, which is this line. We'll see it later. And what happens in between? In the middle, there are many states where the fluctuating factor is not the dry air, but the water vapor content. To see the family of curves, all these lines of curves or straight lines that the diagram has, we'll start with the ones we know best. The dry bulb temperature, which is the normal temperature, the temperature we usually talk about. The relative humidity. But the first thing we have to see is, as in any diagram, when we work in 2D, we can define a point by two variables. We could enter via two variables and know a point. But this is false in the psychrometric diagram. We have to have three. Each psychrometric diagram is made for an altitude, for an elevation above sea level. Changing elevation, diagram changes. In fact, it does. Higher we go, diagram gets smaller. Hence, if we start with an unsuitable diagram for the desired work area, all calculations will be inaccurate and incorrect. This, for example, is for 0 meters above sea level. To work at 100, 200, 300, 400 meters above sea level would be valid. It would be a very accurate approximation. You could already search with a computer. Directly put the altitude and it modifies you. The diagram? But when we work at 2,000, 3,000, 4,000 meters of altitude, it's invalid. We get wrong data. Hence, to access a psychrometric diagram, we need three parameters. The first one is the altitude, and then two of those curves to determine the exact point of the air. All these lines or curves are referred to as isos. A line, iso, indicates that one variable remains constant. In this case, if we have isotherms, it means their temperature is constant, remains unchanged. On analyzing this line, it can be observed that there will always be a measurement of 30 degrees for the dry bulb temperature. This dry bulb is the temperature measured with a standard thermometer, where the bulb can be alcohol, mercury, in contact with the ambient air, the air that surrounds it, which is not dry. The air we have right now around is air that has humidity. It will always have humidity. Having dry air is very complex. We can almost say it's impossible. A very deep drying process would be required, but, well, we call it a dry bulb because its surface is not moistened with water. Well, this thermometer is going to display the dry bulb temperature, which would be the x-axis of the diagram. And if we throw perpendicular lines, completely vertical, all the lines share a variable with a constant value, in this case 40 degrees of dry bulb. Relative humidity is also a variable that doesn't sound like much. Air with 20% relative humidity has little water. Air with 50% relative humidity is normal. Air with 80% relative humidity is very humid. But let's see that this is not true, because we can have air with 80% water vapor that has less water than one with a meter. The isothermal wet bulb lines are not measured with the thermometer we have seen previously, but with a thermometer in which the bulb is placed inside a saturated atmosphere. Here, inside this container, we would have a cotton filled with water, so that water will evaporate, and inside the bulb, inside that container, there will be a completely saturated air, 100% air, with which the bulb is going to measure differently than the first bulb we saw that was in contact with the atmospheric air. Temps they'll give us will be totally different. In fact, if we have air, for instance here, to know its wet bulb, to know the dry one, we'd lower it. But to know the wet, we would send through these inclined lines, we would reach saturation, because the bulb is actually in saturated air, and we would descend, obtaining the value of wet bulb. Wet bulb temperatures will always be lower than dry bulb temperatures, okay? Unless we find an environment where the air is completely saturated. No 100% humidity environment found where both bulbs work the same. In this example, it will always be the same example. We work with 27 degrees Celsius dry bulb. We know where it is. It's here. And this whole line is at the same dry bulb temperature, so we still don't have the point definite, but it tells us it has a 50% relative humidity. We would pass through the 50% line, 27, and we would arrive at this point. To acquire the wet bulb, we would track along the inclined line until reaching saturation, and then descend to the dry bulb, obtaining a wet bulb value of 19.5. We already possess the dry bulb, the wet bulb, and the relative humidity. What would be the temperature of the dew point? The dew point temperature is the temperature at which air must be cooled in order for it to become saturated, so that at the end it has a relative humidity of 50% or 80%. It would become an air with 100% relative humidity. If we take the same air as before, at 2750, we will observe that the dew point temperature would be obtained by projecting horizontally towards the dew line, which will provide us with a value of 15.7 degrees dry bulb. That signifies that the initial air at 2750 degrees has an average relative humidity of 50%. If we cool it down, it would go from 50 to 60 to 70 to 80 to 90 and to 100%. If we lower its temperature from 27 to 15.7, that air goes from having a 50% relative humidity to having 100%. But the air has not changed, it has simply cooled down. As the air cools down, it decreases and can hold less air. Having a 50% relative humidity means that it is halfway full. We could add more water to reach 100%. If we have air at 20%, it means it is filled to 20%. If we have air at 80%, it means it is very saturated. It has 80% of its water capacity. At 50%, it will be half full. To reach saturation and make the air saturate as it decreases, it must be cooled. And to know what temperature that is to be cooled, what we have to do is send this horizontally towards the saturation line. Good. We already know how much relative humidity that air has, that percentage, but really, how much water does air have? Specific humidity lines tell us ISO lines where specific humidity is constant, measured on air axis. If you look here, it talks about specific or absolute humidity in grams of water per kilogram of dry air. This line shares same value, in this case 15, okay? For the case of 2750, the specific humidity would be, we take this point, send it horizontally, and it tells us that it has 11.5 grams of water. As we said before, this air with a 50% relative humidity is at half load. It can hold another 50%, it's a glass half full or half empty. With this, we could achieve, by adding water in the form of steam, that instead of 11.5, it could hold 23 grams of water per kilogram of dry air. By adding water, the temperature remains constant. It is not a real cycle, but it works at a didactic level. We could ascend and we would proceed to 60, to 70, to 80, to 90 and reach 100%. We would achieve saturation by introducing steam into the system without altering its temperature. And this point has 23 G of water per kilo of dry air, which is exactly twice what we found before for a 2750. The isenthalpic. These are the lines we commented on that talk about the energy this mass of air has, and its variation will give us the energy needed to go from one point to another, and based on that, the power. With any given point, 2750, we'd locate and throw it along the same or a similar line, depending on the diagram. You may find two lines or resembling ones, normally two but almost parallel. Not exactly parallel, but close. For the wet bulb, which is the isoenthalpic in this case, we'd find a value in kilojoule per kilogram of dry air. That would be the internal energy. The isocores, if we do the inverse, will give us the density of the air. Why is air density important? If you look closely, there are values, like this water gram per kilo of dry air, kilojoule per kilogram of dry air. Thus, it is crucial to determine the air density. By doing so, we can ascertain that at this juncture, we would be able to determine that the specific volume for this value, 27.50, would be 0.8666 men3. How can we obtain it? Well, at this point, it's between two isochores, exactly between this and this spot. We use a rule of 3 to determine the distances of this point from the isochore. With these values, we apply a rule of 3 and calculate the result as 0.866 cubic meters kilograms. Is this calculation accurate? Why is this important now? Because when we take the inverse, we get a density of 1.168 kilograms per cubic meter. With this value, we can already say that 1 cubic meter of air weighs 1.168 kilo. It weighs very little. 1 cubic meter of water weighs 1,000 kilo. Therefore, air has very little mass. Let's see a couple of examples. At this point, it is necessary to determine all the characteristics of air with a dry bulb temperature of 45 OC and a relative humidity of 30%. If you desire to trim the video, perform the exercise, and we shall observe it. What would be the nature of those particular characteristics? We knew the dry bulb, 45 degrees of dry bulb, always put the last name, wet bulb temp, 28.7. How? Launching from the wet bulb, descending to the dry bulb, we obtain the value of 28.7. The dew point? Well, we cool it down until saturation. We are cooling down, and we go down to that specific value of 23.4. The relative humidity? We already knew her. Absolute humidity, another horizontal to the y-axis. The enthalpy? Through this isoentartic line, 92.2 kilokilo of dry air, density as a function of specific volume, calculated by relying on these two lines, on isocore and isocore. And its density, 1098 kilo m3. Previously it was 1168. Notice how it varies. The density of air varies depending on its temperature and humidity. If we change the temperature, the density varies, obviously. If we add or remove water, weight varies. In the end, density is that, okay? Variations. Another example would be air with 15 degrees dry bulb temperature and 60% relative humidity. By performing the calculations, we will obtain the following values. Take note of how intriguing this is. Previously, with a relative humidity of 30%, our absolute humidity was measured at 0.0018 kilograms per kilograms of water per kilograms of dry air. However, now with a 60% relative humidity, we have much less. We have about a third, Why? Because prior to this, our position on the chart was significantly higher, leading to our absolute humidity being high or higher than it is at present. However, the relative humidity is different. Here is a 60 and inside there is a 30. What I wanted to say before is that relative humidities do not indicate how much water vapor is in the air, but rather how full it is. Because depending on the temperatures, we will encounter air masses that are capable of holding a lot of water vapor and air masses that will hold very little water vapor. When the temperature drops, the air is like a glass that becomes smaller, it holds less. While when the temperature rises, it expands and can hold more water vapor. Relative humidity, as the name suggests, is relative. It doesn't indicate a specific amount, but if it's high or low. That concludes our talk. We await the next video.